Hi, in this video, we're going to talk about Lewis acids and Lewis bases and a little bit about conjugate acids and conjugate bases. So let's get right down to it. So the idea of Lewis acids and bases is different from either the Bronsted-Lowry model, which discusses the issue of transfer of a proton from one reactant to another, or the Arrhenius model, which discusses the production of a hydrogen ion or a hydroxide ion in water. The Lewis acid base model is based on the idea of Lewis structures. And if you recall, in Lewis structures, we have this idea of the octet rule, right? 8 electrons, 8 valence electrons. And that gives stability, right? So that's what we're looking at here, the octet rule, essentially. So here's an example. The aluminum ion, Al plus 3, that's the charge, the typical charge of an aluminum ion, can react with a hydroxide ion in the following way. The hydroxide ion has a negative charge, right? So I'm going to put the negative over here. And notice the oxygen has 8 electrons, 8 valence electrons in any case, 3 lone pairs and 1 bonding pair to a hydrogen. And what can happen is the electron pair from the oxygen can become attracted to the aluminum ion. Now, the aluminum ion is positively charged, so that could, we could explain the attraction in that way. Another way to explain it is the idea that if you have an empty orbital, so if you have an electronic orbital and it doesn't have any electrons in it, you can put electrons into that orbital, right? So if you have an empty orbital for the aluminum ion and the oxygen has a pair of electrons, those electrons can now interact with that orbital and take up some space around the aluminum ion. The result of this is that we now end up with a bond, right? So this pair becomes a bond to the aluminum. Okay. And, overall, what would we expect the charge to be here? If this one's plus 3 and this one's minus 1, plus 3 and minus 1 would be plus 2. So overall, we would expect the whole thing to be plus 2, positive 2. Okay. And what we can see is that with aluminum, it will actually react with 3 hydroxides to form aluminum hydroxide. And this is a precipitate in water. It's not soluble in water. And so what's really happening is you've got these empty orbitals for the aluminum, and then you've got these electron pairs for each of the hydroxides. So there's the electron pair forming a bond to the aluminum. There's an electron pair forming a bond to the aluminum. And there's an electron pair forming a bond to aluminum. So notice this is all about bond formation, right? We're forming chemical bonds. And that may not seem connected to acid-base chemistry, but it turns out it is. So here's how we're going to define. We're going to define when a new bond is formed. The electron pair donor is called the base. Okay. The donor is the base. So that means the hydroxide is the base because it's the one that's donating the electrons to form that chemical bond. The electron acceptor is what we call the acid. Okay, it's called an acid. So the aluminum in this case would be the acid because it's the one accepting the electron pair to form this new chemical bond. Okay, so sometimes atoms will form bonds, each donates one electron. We go over that in Lewis structures. But sometimes one species will have a pair, the other one won't have any. They form a bond using both electrons from the one that has the pair. The one that has the pair is called the base, and the one that doesn't have the pair at the beginning is called the acid. Lewis acids and Lewis bases. Okay, and that's essentially the idea. Now let me show you one more example. Let's take something very simple, H plus and OH minus. Okay. Well, let's draw the Lewis structures. Hydrogen ion doesn't have any electrons at all. In fact, it doesn't have any valence, but it also doesn't have any electrons at all. The hydroxide ion has 8 electrons, 8 valence electrons. So here's what's going to happen. We're going to push. I'm going to notice I'm using an arrow drawn in between the 2 electrons to show the direction of the electrons. The electrons are now moving towards the hydrogen ion. Now, obviously, they have to be close for this to work. It's not going to move, 5 times the distance, but of the size of the species. But we're going to get a new bond. And all we need to do really is just to notice that there's a new bond, a new covalent bond, and it has a pair of electrons. Where did the electrons come from? They came from here. There's our source of the electrons. So this is the base, a Lewis base, we call it. We specifically call it a Lewis base. And the one that accepted the electrons, this is the acceptor. We call that the Lewis acid. Okay, and there you go. So that's essentially a little intro into the idea of Lewis acids and Lewis bases. Now, anything that is a Bronsted acid is also a Lewis acid. So all Bronsted acids are also Lewis acids. And all Bronsted bases are Lewis bases. Okay, because whenever you have a Bronsted acid or Bronsted base, the transfer of the proton results in a particular formation of a bond. So that's going to also give you a Lewis acid and Lewis base. But it doesn't work the other way around. So the idea is that if something is a Lewis acid, it may not be a Lewis base. I'm sorry, if it's a Lewis acid, it may not be a Bronsted acid. It may not be Bronsted acids. Likewise, Bronsted bases may not be Lewis. Oops, sorry, I meant Lewis here. Getting confused here. Lewis bases may not be Bronsted bases. Okay, so let's take a look at an example. Okay, so identifying Lewis acids and bases and reactions. In each row, check off the boxes that apply to the highlighted reactant. So in the first one, they highlight HBr. Now we would recognize HBr is definitely a Bronsted acid, right? It's a strong acid, definitely going to protonate whatever it reacts with, right? So notice here what happened. The HBr is transferring an H plus to the ammonia to give you Br minus and NH4 plus ammonium ions. So it's definitely, HBr is definitely a Bronsted acid. But we also want to show that, in fact, it's also a Lewis acid. And here's how we would do it. I'm going to actually come over here. Oops. And show you. So here's what they're showing. So I'm going to write the equation first. And what I want to show you is that, in fact, if we draw the Lewis structures of each of these species, okay, so there's our Lewis species, our Lewis structures of everything. Look what happened. There's a new bond here, right? A new bond formation. So that's a dead giveaway that there's some sort of Lewis acid base chemistry going on. So let's see if we can figure out what the source of the electrons for that new bond was. If we look at it, the Br minus has all of its electrons. It had, these 6 here, plus there's a pair right there for the bond to hydrogen. The hydrogen now is attached to the nitrogen. See that new bond? That's the new bond. It came from this and this. Which one do you think had the electrons? It's the nitrogen. This is the one that has the electrons. It has the lone pair. The hydrogen actually gave up its electrons to the bromide. Now the bromide has all 8. So that means this is the electron source of the new bond. And so this is the base. This one formed a bond to the nitrogen, but it didn't use its own electrons, so it's the acid. And let's be careful, this is called a Lewis acid. Okay, so the HBr is both a Bronsted acid and a Lewis acid. As I said, if something is a if something is a Bronsted acid, it is necessarily a Bronsted acid, a Lewis acid as well. Let me say it one more time. All Bronsted acids are Lewis acids. Okay. So once you identify that something is a Bronsted acid, you also know it's a Lewis acid. So let's take a look at the second one here. HCN is reacting with CH3NH2, that's methylamine, reacting with hydrocyanic acid. So clearly you can see there is a transfer of a hydrogen ion from the HCN to the CH3NH2, the methylamine, right? You have this new bond over here, this new NH. It's an H plus. So that's definitely a Bronsted acid. The HCN is donating the H plus. But again, there's a new bond over here. The nitrogen was bonded to 2 hydrogens. Now it's bonded to 3 hydrogens. So that means that it's a new bond. So we are now talking again about a Lewis acid and a Lewis base. Okay, so both of them. And then the aluminum here. Now this one, there's no apparent transfer of an H plus occurring, right? You don't see an H plus going anywhere. H2Os are attaching to the aluminum. So it's not a Bronsted-Lowry acid or base. But what about a Lewis structure? The aluminum doesn't have any bonds. Now the aluminum is bonded to water molecules. Well, there you go. There's bond formation. Where do you think the electrons came from? Well, what you have to do is you have to figure out what the Lewis structures are. Okay. So you got aluminum plus 6 waters. Well, water, what is water? Water has an oxygen at the center with 2 hydrogens and then 2 lone pairs. So really what's happening, okay, there's your product over there, is the water is the source of the electrons. The oxygen, in fact, is the source of the electrons. That's what's causing the formation of the bonds. Okay, so this is the base. and this is the acid. But specifically, we want to say that this is the Lewis base and this is the Lewis acid because there's no transfer of an H plus here. It's merely the formation of a new bond. So the aluminum in that case is called Lewis acid. Okay. Now, there's one other type of problem that I want to show you, and it has to do with identifying qualitative properties of acids and bases. And this is somewhat related to Lewis acids and bases, but not all that much. So let me go through this a little bit here. Predicting the qualitative acid-base properties of metal cations. So this is specifically of metal cations. So the metal cations would be like sodium, and iron, those ones right there. Okay. Now, if we look at a salt, what we've learned before is that salts can be acidic, basic, or neutral. It depends on what the salt is composed of. Remember, salt is the product of an acid and a base reaction. Acid plus base gives you water and salt in general. So that means the salt has the conjugate acid of a base and a conjugate base of an acid. It has built within it an acid and a base. They're conjugates. So the only issue is which one is stronger. If the conjugate acid in the salt is stronger than the conjugate base, it'll be acidic. If the conjugate base is stronger than the conjugate acid in the salt, it'll be basic. And if they're equal, it'll be neutral. Okay, remember neutral is pH 7. So in this particular one right here, we have sodium and then we have hypochlorite, ClO4 minus. And we want to know whether this is going to be acidic or neutral or basic. Oops, sorry. There we go. Okay, here's how we go about it. You deconstruct the salt into its two component ions. So let's take a look at this one. Okay, so the first thing you do is you deconstruct it into the ions. Okay, so you have a sodium ion and a hypochlorite ion. You then identify what the acid and base these came from, right? So let's remind ourselves, if you take an acid and you react it with a base, you get water and you get a salt. The salt has a conjugate acid and the conjugate base within it. Okay. Now, in general, the conjugate acid is the positively charged one. So that would be the sodium ion. And then the conjugate base is generally negative. So that would be the hyperchlorate or perchlorate. Okay. So those are your conjugates. So the question then is, are they of equal strength as an acid and a base? Or is the acid stronger than the base, or is the base stronger than the acid? So here's how we go about that. The way we determine this is by considering all of your strong acids and your strong bases. You just want to have this in a table next to you or memorize them, which would be even better. The strong acids are HCl, HBr, HI, HNO3, HClO4, and HClO3. That's generally considered the list of strong acids. Okay. Now, these strong acids are going to have very weak conjugate bases. Okay, so what's the conjugate base of HCl? Cl minus. It's just the negatively charged ion. So the same would go for all these. So you just memorize those. Okay, the strong acids will have very weak conjugate bases. Weak meaning they don't have much effect on acidity. Okay, then you memorize your strong bases. And there are a couple of others. There's SROH2, and then there's BaOH2. Okay. And what are the conjugate acids of those? Li plus, Na plus, K plus, Rb plus, Cs plus, Sr plus 2, and Ba plus 2. Okay. These are going to be very weak. Okay. So here's the way you can approach this. We have a sodium ion. That is the conjugate acid of a strong base. So it is very weak, does not have much effect on acidity. We also have perchlorate. Perchlorate is right here. That is the conjugate base of a very strong acid. Therefore, it's a very weak acid. I'm sorry, very weak conjugate base. So in fact, both of these are very weak. So if they're very weak, it's not going to be acidic or basic. So it's going to be neutral. Okay. So notice it's essential that you have these two lists. If you don't have those two lists, you would have no way of knowing what the effect of acidity would be for these particular ions. Okay. All right, let's take a look at the second one on this. So the second one is NaNO2. So notice there's your salt, sodium ion. Again, we already decided that sodium comes from a conjugate. It is the conjugate acid of a strong base, so it has no effect on acidity. So the sodium is not going to affect it, so it's not going to be acidic. The only question is, what about this other ion, the NO2 minus? Be careful, this is not NO3 minus, the nitrate ion, this is NO2 minus. NO2 minus comes from a weak base. If it comes from a weak base, that means the conjugate acid is going to be relatively strong. Okay. I'm sorry, it comes from a weak acid. Therefore, the conjugate base is going to be relatively strong. So let's make another little list here. These ones you don't really have to memorize, but it's good to actually kind of look at them. So these are weak acids. HF, HC2H3O2. Okay, there's a few there. Let's see if I can find H2S would be another example. Those are just four of, HCN. Okay, so there's some weak acids. So now these are going to be relatively stronger conjugate bases. Okay, oops, sorry, that's a 2. NO2 minus, F minus, C2H3O2 minus, HS minus, notice you're getting rid of the H plus, CN minus. So these are relatively strong conjugate bases, which means that they will make the solution basic. Okay, so now when we come back to NaNO2, here's what we have. This is the salt. You have Na plus and NO2 minus. Well, this one comes from a strong base. This one comes from a weak acid. Now this one, remember, the positive one is what we call the conjugate acid. It comes from a strong base. No effect on acidity. Okay. Now this one right here it comes from a weak acid, right? It comes from HNO2. This is the conjugate base. So this one is somewhat basic. It comes from a weak acid, so it's actually going to be somewhat basic. So now here's what we have. We have something that is not acidic, something that is basic. So overall, it's going to be a basic solution. Okay. So sometimes salts will actually make water acidic. Sometimes they'll make water basic, depending on what that salt's comprised of. You have to figure out what it came from in order to answer that question. There's one more, which is iron with bromide, FeBr2. Okay, FeBr2. So let's take a look at that one. Okay, remember, when you break this up, you're going to get iron ions and bromide ions. Dissolved in water. And the question is, what are they going to do in water? Well, again, this is a salt. This is the conjugate acid. This is the conjugate base. So what did the conjugate base come from? It came from HBr, which is a strong acid. And what we said was that if it comes from a strong acid, it has little effect on acidity. So it's a very weak acid. I'm sorry, very weak base. Okay, if it comes from a strong acid, it's going to be a very weak base. The iron, on the other hand, now that's not so clear because we didn't really see what that came from. So here's where we're going to approach this. This is where it connects into Lewis acids. The transition metals. So that would be iron, cobalt, lead. Actually, lead's a post-transition metal, but it behaves very much like a transition metal. Cadmium, chromium, okay? The transition metals behave as Lewis acids, right? We talked about that in the previous problem, that those metals like aluminum again is not a transition metal, but it behaves in some ways like a transition metal. And so what does that mean? What it means is they react with water in order to become what's called a complex ion. Okay? So they're behaving like a Lewis acid. So the iron is going to do the same thing. The iron, if you put it into water, it will also form bonds with the water. Now, the number that it forms is not clear, but it might be 6. It's something you have to look up. But in any case, this is behaving as a Lewis acid. So if you have a transition metal or aluminum, and it's in a salt, then the transition metal will behave like a Lewis acid. So if it's behaving like a Lewis acid, that means the solution is going to be acidic because the bromide comes from a strong acid is not going to have any effect on the acidity. Now, there's one situation here that I haven't looked at, and that is what happens if you take something that's somewhat acidic and you combine it with something that's somewhat basic. So for example, the iron +2 is acidic, and then the nitrite is basic. That gets a little more complicated. To some extent, they cancel each other out, right? If you take an acid and a base, it becomes neutral, but it's a little bit more involved in that. You have to actually do a calculation to figure out how strong the acid is and how strong the base is. So it's not so obvious how to deal with that. So most of the problems we look at, either neither are acidic or basic. So that's not acidic, that's not basic. So overall, it's neutral. Or sodium is not acidic, but nitrite is basic, so it's basic. Or let's do ammonium, actually. Ammonium comes from a weak base. Okay, oops, we don't need the plus there. I'm writing the formula. Or this one's acidic and this one is neutral, so overall it's acidic. So those are the 3 cases that we would look at. Okay, so as I said, the important part of that I would recommend is that you just have a list, memorize the strong acids and strong bases. That way you can tell whether the conjugates are strong or are weak. They will be weak, the conjugates will be base. But if it comes from a weak acid or a weak base, then the conjugates will have an effect on the acidity. Okay, all right, well, take care.